Hello, my name is Alessandra Quaviva. I'm a PhD student at Chalmers University of Technology, and today I would like to introduce you the topic of my PhD research, and the topic is high-performance cooling electric motors for electric vehicles. So electric vehicles are happening. We reached 2.1 new electric units in 2019, which accounts for about 2.6% of the global sales, which it's not a huge percentage, but if you look at the trend, which is a 40% market growth year on year, and if you look at the predictions from several sources, it looks very positive. So in 15 years from now, we could have between 9 and 18% of the total market. What is holding up the expansion of electric vehicles? Well, there are mainly two bottlenecks, I would say. One is the fact that the energy storage is still problematic. So the lithium-ion batteries are costly, they are heavy, and the lifetime is still can be an issue. And the other problem is the charging infrastructure, which is also not as spread as it would be needed, and it needs huge investments. So the electrical car or the electric vehicles is driven by an electric drivetrain, and the electric drivetrain has an electrical machine which is generating the torque. So why are we so interested in pushing the technology for the electrical machine? Well, as you know, in the automotive industry, you start producing millions of parts, then cost becomes really important, and having high performance with engineered parts and low cost is really important. So also the electrical machine is moving towards new technologies. So how does an electrical machine work? Well, we have two main parts. One is the stator. You can see on the top left figure where there is a part missing inside. That's the outer part with the copper and the iron is the stator. The stator is responsible for generating a rotating magnetic field. So the copper conductors there's current passing inside, and this current generates a rotating magnetic field, which is contained within the iron, which has high permeability and allows the magnetic field to stay within the iron. And then we have two main types of machine. We have many, but let's contain it to two types. What is called induction motor and what is called PM synchronous motor. The induction motor is basically the rotating magnetic field induces current in some conductors which are placed on the rotor, and the currents induced in this rotor they interact with the rotating magnetic field itself, and they generate torque. While the PM synchronous motor, it has magnets on the rotor, and these magnets generate a magnetic field themselves, and yes, basically they interact in such a way that torque is produced as well. So here on the bottom right, you can see a permanent magnet synchronous machine electromagnetic simulation. So you can see that there is a magnetic field which is rotating, and it interacts with the rotor magnets. So what are we looking? What are the requirements? How would like to have the perfect electrical machine in an electric vehicle? Well, we wanted to have very high efficiency. We want to maximize the vehicle driving range. We want that all the energy from the battery goes straight into the wheels. We want it to be small and light. So we want to have high power density. For the same volume and weight, we want a big power. We want it to be safe and to last long. So we want it to be reliable. And of course, we wanted to have it low cost. So we want to utilize the materials to the maximum and have a low cost manufacturing. So how do these two main electrical machine place? Well, usually the permanent magnet synchronous machine has intrinsic higher efficiency and higher power density, so smaller size and weight. And you pay this with being a bit more expensive, and you pay it with the reliability, which there are some reliability issues related to having the magnets. But what if with manufacturing we can improve this these two, the cost and the reliability of PMSM, which is already the main technology that is used in vehicles. So there is a particular way of winding this machine, which is called tooth coil winding. I will not go into the details, but basically it gives you intrinsic reliability, and it's easier to produce because you can see each tooth of the stator as one single coil. And yes, so basically we get the manufacturing process smoother. So with we decrease the cost and we get a bit higher reliability. But as well, there is the possibility, you can see that there is some space left in between the two coils, in between each of these two coils. And this space can be used for cooling. And most of the losses, most of the heat generated during the operation is generated within those copper conductors. So you see, it's very important if you want to push power density to cool. So there are different cooling types. You can have a cooling jacket, so external. You can have a hollow shaft, so through the rotor you cool the rotor. You can have direct winding cooling, so you what we were just talking about. You directly go and try to cool the copper conductors. You can have a fluid bath, so the whole motor is immersed in oil. Or you can have a fluid spray, so you spray on some particular parts. But there are two main types of coolant. One is oil-based, and the other one is basically water. Well, every time you have direct contact with electrical parts and mechanical moving parts, you want to have oil because oil is an electrical insulator. And it's a lubricant itself, so you wouldn't damage the machine by having oil. But one must say that water is a better coolant. It has better cooling properties than oil. So in my case, I decided to use oil because this is the solution I'm proposing. So basically, we have a cooling channel in between the two coils, and we have some cooling channels in the stator iron, which are placed in such a way that it doesn't affect the magnetic performance of the machine. So you can see here how the oil is pushed from one side to the machine into parallel paths, and it goes all the way out, and you have oil in the end parts as well. Well, and the manufacturing process is also quite simplified. I mean, it's producible in a way, so you can assemble the stator iron. You insert the windings within the stator, and then you place these sticks in between the coils. Then you pot the machine. Potting is a process which basically you use these epoxy resins to make the whole thing a solid piece, and also you improve mechanical strength to vibrations, you improve heat transfer, but also you can use it to shape some cooling channels, as you can see here. So If you want more details, there is a lot about these machines, how it's built, simulations and results. That we have published 2 papers. You can find them below. But I'm just going to give a glimpse about the results. So torque is we could reach above 140 Newton meters, which for the size of this machine, which is a 50 kilowatt machine, it's 180 millimeters diameter. It's quite good, and we could hold that torque for which is a very high current density for about 30 seconds. And yeah, without the temperatures within the machine exceeding the maximum temperature. So the cooling performance was proven to be effective, and also the machine itself. We have simulated the efficiency and we have measured the efficiency, and the efficiency matches quite well with the simulations, the one we measured, and it can go up to basically 95%. So you have 100% of the energy coming from the battery, and you get 95 up to 95 directly to the wheels. So this is just to give you a brief understanding about what I'm doing, and thank you for listening. And yes, if you're interested, I will be glad to explain more.